All right, so with that being said, I'll read the aim. So our lesson today is how do we model displacement with the damped harmonic motion function. So this is in opposition to the simple harmonic motion function, which we talked about last time. Damped harmonic motion, as we'll see, is a more accurate depiction of what happens in reality or in physics, right? Okay. But yeah, with that said, can someone read the do now for us? You can just unmute yourself and start reading.
A mass is suspended from a string. From a spring. The spring is compressed a distance of 4 centimeters and then released. It is observed that the mass returns to the compressed position at 1/3 seconds. Should I go on?
Oh, we'll go to Lexi for here.
Okay.
I think raise your hand. Yeah.
A, find a function that models the displacement of the mass. B, sketch one period of the graph of the displacement of the mass.
All right, thank you for that. So we're gonna go over the solution. So I'm gonna scroll up. All right, so first thing to note is that we're given that the spring is compressed. So that should make you think of cosine. Because cosine starts at its max or min, right? Sine starts at 0. Okay, so this is a cosine curve. So we'll use this y equals a cosine omega t formula. Period is 1/3 of a second. So, right, that you have to read into that. Like it says, the mass returns to compressed position at 1/3 of a second. So another way to say that is that's the period, right? So with that, we can solve for omega, right? 1/3 equals 2 pi over omega. Cross multiply, you get omega is 6 pi. Okay. Lastly, the amplitude is 4 because we're given that it's compressed a distance of 4 centimeters. So yeah, it would be 4. Okay. So therefore, your formula will be y equals 4 cosine 6 pi t. Okay, that's for part A. And then for part B, I made a chart here. So 0 to 2 pi. I write t coordinates because we're using cosine t, not cosine x. Subtle difference, but yeah, just wanted to be true to that. Next, we have the x coordinates for the 4 cosine 6 pi t curve. And for that, you just divide each of these coordinates by 6 pi. And if you do that, you're going to get 0, 1 over 12, 1, 6, which I rewrite as 2 over 12, and then 1/4 for 3 pi over 2, and then 1/3. So I rewrite everything in terms of denominator 12 just to, if I were to graph this on paper, that would be easier. But I just showed the Desmos graph here, actually. But for the y coordinates, it's 1, 0, negative 1, 0 normally, and then we have to multiply by 4. So we get 4, 0, negative 4, 0, 4. Okay, so your coordinates 0, 4 is here, 1, 12, 0. Then we have 2 over 12, negative 4, then 1/4, 0, and then that's followed by 1/3, 4. Okay, I think there was some rounding with rounding error with Desmos, but this should be 2.5 or 0.25, right? Because 1/4. But they showed 0.2499. But yeah, these should be your coordinates here. All right, does anyone still need the solution? You can speak up or type. All right, if not, then I'll move on. Okay, so as the aim says, right, today we're going to talk about damped harmonic motion. Now, as I said before, damped harmonic motion is a more accurate model of what actually happens in reality. So simple harmonic motion, right, that model, cosine or sine, it goes on forever, right? The amplitude stays at whatever the amplitude is, right? Let's say it was like 4 cosine t, right? It would stay at 4 and negative 4 forever, right? Which is not accurate because, as we know, like if you have a pendulum or like a spring, right, it's eventually going to stop its motion. Okay. That's where damped harmonic motion comes in. So this, in this model, the amplitude actually tends towards 0. Okay. All right. So here it is. Here's the definition. Would someone mind reading this for us?
If the equation describing the displacement y of an object at time t is y equals ke to the negative ct power sine omega t, or y equals ke to the negative ct cosine omega t, c is greater than 0, then the object is in damped harmonic motion. The constant c is the damping constant, k is the initial amplitude, and 2 pi over w is the period.
All right, thank you for that. So a couple things to note here. One is, so normally for simple harmonic motion, right, we would have a sine omega t, right? So note here that instead of a, the amplitude, we're given k times e to the negative ct. And this is where, this is the major difference, right? It's because the amplitude will eventually stop or tend towards 0 because e to the negative ct, e being Euler's number from algebra 2, if you remember that, that was like the constant 2.71828. It's used to describe exponential growth or exponential decay sometimes, right? Could be used in other contexts, but in this context, it's used to describe exponential decay, right? So e to the negative ct, that graph will tend towards the x-axis, which the graphs we'll get to in a bit, but yeah, so this is exponential decay, and this is what causes the amplitude to eventually decrease to 0. Outside of that, you have a couple of new parameters. C is the damping constant, K is the initial amplitude, that's where the object starts, right? Like that, the max amplitude basically. And then 2 pi over omega, that's the same as simple harmonic motion. So.
Did you say that E is 2.7?
Yeah, E is Euler's number. It's about 2.71828. We're actually going to get into how to derive that number and like give context, more context to it in a later lesson in the year. But yeah, E is 2.71828 about. All right. Does anyone still need this definition? You can speak or type something.
Yes.
I do.
I need it.
All right. Just let me know when you're done, please.
I'm done.
Yeah, I'm done too.
Okay. Does anyone still need it? Okay. I'm going to move on to the next example or exercise. So for this one, I'm going to have you graph. Well, for the sake of time, I think I'll just, yeah, let me see. Oh, let me read it first. So on your graph calculator, graph the following functions over domain -2 to 2, range -3 to 3. And I'm going to ask you, what do you notice about the amplitude? So in part A, I would first want you to graph just 2 sine 8 pi t and e to the negative t. And then part B is the damped harmonic motion formula. Okay, 2 times e to the negative t sine 8 pi t. And as you notice, right, this is the product of this sine function and this exponential decay function. So if you multiply this and this, you get part B. And yeah, you can see like part of the graph on the screen already. But yeah, I'll give you 2 minutes. If you have a graphing calculator, or you can, if not, you can go to Desmos, graph these these 3 functions. But yeah, I want you to graph these 2 first, and then graph part B. Okay, so again, take the next 2 minutes to graph these 3 functions, either on your graph calculator or Desmos.
Wait, when you graph 2 sine a pi t, is this supposed to be inside the parentheses, like the t?
It doesn't have, like, you could do either.
Does it change it? Or does it not?
Mm,
I
well,
tried.
here's what I have on my calculator. I just, yeah, it's inside the parentheses, but I don't think it'll matter. Yeah, because in the end, you're just multiplying 8 pi times x. Another thing to note, like, you should have it in radians because I don't think it'll work with degrees. Or like it could work with degrees, but you would have to change your scaling. All right, so it's all right if you're not done yet. Let me just show what I did on Desmos. Okay, so in red here, as you can see, I have 2 sine a pi t. That's this red graph. That will be simple harmonic motion, right? It goes on forever. Doesn't change the amplitude, right? Then we have in blue e to the negative t, which is exponential decay. That's this blue curve right here, which tends towards the x-axis. And then in purple, it's our damped harmonic motion formula. And here I stopped at +2. But yeah, as you can see, right, the purple graph the amplitude does change. And the way we get that is you just multiply the simple harmonic motion formula with the exponential decay formula. Okay, so for example, let me zoom in here. Let's say you had this, this value here. I'm just going to choose a random value. So you have 0.56252. And then, so that's our red graph, right? And then for the blue graph, the exponential decay, it's something like 0.57 for the y value, right? So 0.57 times 2, that will produce the y value for the purple curve. Okay, so the purple curve should be about like 1. Okay, so it's 1.1405. Okay, so yeah, let me just emphasize the red curve time, the product of the red curve and the blue curve will produce the purple curve, which is our damped harmonic motion formula. Okay. And as you can see, right, the blue curve eventually, as it's decreasing, right, the purple curve also decreases, right? That's what's causing the amplitude to decrease over time. Okay. All right. Yeah, outside of that, let me, I'm going to talk about one of the homework questions, or sorry, not homework questions, classwork questions, question 3. Oh, sorry, in the chat, the product of the red and blue is purple. Yeah, so yeah, if you multiply the red function, which was 2 sine a pi t with e to the negative t, which is the blue function on Desmos, then you get this, right? This times this, and then I did 2 times, I switched it, right? But yeah, it's the product. If your graph doesn't look like that, make sure you have these, yeah, your window should be this, okay? It's most likely the window, that's the problem. Okay, so -2 to 2 for x min, x max, range is -3 to 3. And yeah, make sure you use ratings as David said. Okay, all right, but yeah, let me get to the third question on the classwork. This was difficult, so I did want to provide a hint. So yeah, I mean, at the bottom is the answer, but I want you to actually work through it on your own, try it on your own, and then we'll go over it tomorrow. Okay. All right, can someone read this question 3?
A stone is dropped in a calm lake, causing waves to form. The up and down motion of a point on the surface of water is modeled by the dampened harmonic motion. After 30 seconds, the amplitude has been reduced by 80%. Find the dampening constant to the nearest 10,000ths.
All right, thank you for that. So a couple things that make this problem hard. One, you have to recognize that in the damped harmonic motion formulas, as I write here, the amplitude is associated with k times e to the negative ct. Okay, so yeah, in simple harmonic motion, it's A, right? In A cosine omega t. For damped harmonic motion, it's K times e to the negative ct. And then the rest is like the cosine curve, right? But this is what is going to change the amplitude, okay? So the original amplitude is, we can just write that as K times e to the negative ct. And then the amplitude after 30 seconds is K times e to the negative c, and then just add 30 to t, right? So t plus 30. All right, that's the first part that makes this question difficult. The other part that's difficult is, or tricky is, it says the amplitude has been reduced by 80%. So we just have to be careful in how we translate that into an equation. So if it's been reduced by 80%, let's say your original was 1, right? The new amplitude after 30 seconds would be 0.2, right? You take away 80%. So it's been reduced by 80%. So 1 would become 0.2, okay? So I write that here. In 30 seconds, the amplitude is 20% of the original. Okay, that's how you interpret this part, okay, reduced by 80%. Okay, with that, we can set up the equation. So this is the amplitude after 30 seconds. Let me zoom in here. So K times e to the negative c times t plus 30. That's equal to 1/5 of the original amplitude, right? That's equal to 0.2 of the original, right? If you want to use numbers, right, let's say, again, the original is 1, and then the new one would be 0.2, right? So here in this equation, we would have 0.2 equals 1/5 times 1, right, which does match up. Okay, and then our job is to solve for the damping constant, which I remind you is the parameter c. Okay. But yeah, I want you to try that on your own. It's just it's gonna involve some exponential rules from algebra 2, and then also natural logarithms. Okay, we're gonna take the ln of both sides eventually. Okay, yeah, this is a a good start for question 3. Questions 1 and 2 are relatively simple. It's just plugging in numbers and solving. Nothing really new there besides using the formula. But yeah, we're gonna go over all these problems tomorrow in class, and then homework is due tomorrow. So you'll have time to do that. But yeah, one of the homework questions is very similar to question 3 here. Okay, just FYI. All right, but yeah, that's all the time we have for today. And if you have further questions, you can ask me during SGI at 2:47. That's in 5 minutes. But yeah, if you have no other questions, you're free to go, and I will see you all tomorrow. Take care.
Have a good day.
All right, thank you, you too.
Have a nice day.